Hello, this is OCR Further Statistics. We're in Non-parametric Tests 1 and the third video on the Wilcoxon signed rank test. As before, occasionally it's a good idea to stop and work some things out for yourself or review what's just been covered. Whenever you see this symbol, pause the video and follow the instructions before continuing to watch. The single sample sign test is all very well, but you're ditching a whole load of information. These two sets of data would give exactly the same result for a null hypothesis that the median is 15. Pause the video and try a single sample sign test on both sets for a 5% significance level. OK, let's just check your hypothesis test. Here are the null and alternative hypotheses. Have you remembered to define x? X is binomial 11, 0.5. There are 8 results above the median, and the p-value is 0.1133. That's greater than 0.05, so we reject the alternative hypothesis. There is insufficient evidence to conclude that the median score has increased. What about set 2? Of course, we get exactly the same calculation and therefore the same conclusion for set 2. All we are counting is how many scores are above the median, which is the same for both sets. But these two datasets are clearly very different. Can we use more of the information without making too many assumptions about the distribution? Let's look at how far the data are from the median. The idea behind the Wilcoxon test is that values further from the median make a greater contribution than values close to the median. I've highlighted the negative ones below the median so we don't lose sight of them. We're going to order them according to how far from the median, so we'll start by making them all positive, and then we'll rank them. Finally, we add up all the ranks that were above the median, the unshaded ones. That comes to 59. And add up all the ranks that were below the median, the shaded ones, which comes to 7. Our test statistic t is the lower of these two numbers. Note that the sum of W plus and W minus is just the sum of the ranks, so is fixed by the sample size. For a sample of size 11, that's 11 times 12 divided by 2, which is 66. So the decision to take the smaller of the two numbers is just an arbitrary decision which we need to follow because that's the way the tables are set up. Now let's think about what t means. Remember that the total of W plus and W minus is fixed by the sample size. If the data is representative of the null hypothesis, it will be roughly symmetrical about the median, and W plus and W minus will be roughly equal, about half the fixed number, in this case 66. If the median has increased, we'd expect W plus to be higher and W minus to be lower. If there is enough difference, we'll want to reject H0. So we're looking for a small value of t. If it's not small enough, we won't reject H0. We have a sample size of 11, so look in the n equals 11 row. It's a one-tailed test, as we are testing to see if the median has increased, and the 5% level, so this column. This is the critical value, 13. Remember, we're looking to see if t is small enough to reject the null hypothesis. So the critical value is the largest t can be and still reject the null hypothesis. Our value of t is 7, which is smaller, so it's in the set of values which leads to rejection of the null hypothesis. So, the critical value is 13, and RT is less than 13, so we reject the null hypothesis. And write the conclusion in context. OK, that's a lot of steps, so pause the video while you go back over the method on this page and rewind it to listen again if necessary. OK, now let's try this with the second set of data. Pause the video while you try it for yourself first. So, first we find the differences from the median of the null hypothesis, which is 15, and highlight all the negative ones. Then we make them all positive. Next we rank them. And now we add up all the ranks above the median to get W+, and the ranks below the median to get W-. Now check that W+ and W- add up to the sum of the ranks, which we know already is 66. The lower of the two values, noting that both numbers are positive, is our test statistic T. And we check it against the critical value, which of course is the same as before. So now T is greater than the critical value of 13, so it's too big and we don't reject the null hypothesis. There is insufficient evidence to suggest that the median has increased. You can see that W+ and W- are much closer to each other in this sample, which suggests that the median could still be 15. Now, of course, these were carefully created samples to illustrate a point. Don't for a minute think that this was real data. But they show that the Wilcoxon test holds more of the information. In this case, not actually how far the data is above or below the mean, as we're still using ranks, not the data itself, but at least which side has data that is further away. My skewed samples show that if the data is skewed, then although you should have equal numbers above and below the median, how far above or below will not be even. This could lead you to conclude that the median has changed when it hasn't. So you need to know that the population is symmetric. However, it doesn't need to be normal. And this test is powerful, so it's good to use even when other tests would be valid. So if the sample is large or you know that the population is normal. And finally, don't forget that you can use the formula for the nth triangle number to check what the sum of W+ and W- should be. Here's a summary of the steps. You might like to pause the video and make a note of them. That's the end of this video on the Wilcoxon signed rank test. Why not see if you can find some real data to try it out on? This test is used extensively in psychology, so if you have a psychology department in your school, ask them for some data. Or a biology teacher might have some suitable data. Or your maths teacher might be able to provide some suitably anonymised test scores. The next video looks at what you do if your sample is too large for the tables of values.